Hello everybody, this video is on preparing for titration. An experiment is conducted to investigate the concentration of a 100 milliliter solution of sodium hydroxide. Exactly 50 mL of a 0.2 mol per liter solution of hydrochloric acid is required to neutralize the solution. So we can begin by writing a balanced chemical equation. So you've got sodium hydroxide solution plus hydrochloric acid solution, and this produces salts, which is sodium chloride and water. The equation is already balanced, so the sodium hydroxide and hydrochloric acid will react in a 1-to-1 ratio. The number of moles of hydrochloric acid used is its concentration multiplied by the volume in liters, and this is 0.01 mole. Therefore, the moles of sodium hydroxide that was in the solution, which is 100 mils, is also 0.01 moles, a 1-to-1 reaction ratio. Therefore, the concentration of the sodium hydroxide solution is simply the number of moles present divided by the volume in liters, which is 0.1 mole per liter. I'll leave my answer here in 3 significant figures. The reason why I've gone through this example before we go through titration is because I want to emphasize the importance and the reason why we conduct titration experiments. In this particular example, we've been told that exactly 50 mL of the acid solution is required for complete neutralization. But how do we know that all of the sodium hydroxide has been neutralized? The answer is titration. Titration is an analytical technique that is used to determine the concentration of a solution. And in that previous example, the concentration of sodium hydroxide will be determined using titration. Titration is a quantitative technique because it involves numerical measurements and calculations, and it is used to calculate the concentration of either unknown acids or base solutions. There are 2 types of titration: an indicator-based titration, which will be the focus of this video, and a conductometric titration method, which will be discussed in a separate video. Titration requires a solution of accurately known concentrations to start with. In the example we discussed, we require a hydrochloric acid solution of exactly 0.2 mol per liter. This solution of known concentration is called the standard solution, and every single titration requires the preparation of a standard solution. If we don't know the concentration of the solution, then we will never be able to find out the concentration of the sodium hydroxide. If the unknown solution that we are trying to determine the concentration of is basic, then the standard solution will have to be an acid solution. The converse is also true. If the unknown solution is an acid, then the standard solution should be a base. Titration is also considered as a volumetric analysis because this analytical technique aims to measure the volume of the standard solution that's required to exactly neutralize the unknown solution. In the example we discussed, this volume was exactly 50 milliliters. The volume required for complete neutralization is called the Titre volume. So the 50 milliliters of hydrochloric acid is a Titre volume for this particular titration. The first step to any titration involves the preparation of the standard solution. There are 2 types of standard solutions: primary standard and a secondary standard. A primary standard is prepared using pure chemicals, whereas a secondary standard, its concentration is determined by using another primary standard solution. Not every chemical is suitable to be used as a primary standard solution. There are numerous properties a primary standard substance should have. It must have a high purity and an accurately known chemical composition. If the standard solution involves using an impure substance, then the concentration of the standard solution may not have been accurate, which will lead to an inaccurate calculation of the concentration of the unknown solution. The primary standard should be free of moisture. There are lots of substances and chemicals which can absorb water quite readily from the surrounding air. In the case where water is absorbed, the purity of the substance will decrease because there's some amount of water in that substance. And again, this would lead to inaccurate calculations of concentrations after the titration. The standard must also be chemically stable. We don't want the standard to chemically react with substances in the solution before the titration itself has taken place. The standard must be readily soluble in pure water. In the end, we want to create a standard solution, meaning that the substance should be able to dissolve quite easily in pure water. A primary standard should ideally have a high molar mass or molecular weight. The number of moles of a substance is given by its mass divided by its molar mass. When we have a large molar mass, any variations in mass when we are weighing the substance will result in a smaller change in the number of moles. Not all acids and bases are suitable for the use of a primary standard. Concentrated hydrochloric acid should be avoided as it is volatile. There can be partial losses of hydrochloric acid in the form of gaseous hydrogen chloride. Sodium hydroxide, which is a very common strong base, is not suitable as a primary standard because it is hygroscopic, which means it readily absorbs water. The absorption of water from surrounding air will reduce the purity of sodium hydroxide. There are a few examples of suitable primary standards. For acids, we like to use benzoic acid and oxalic acid. For bases, we like to use anhydrous sodium carbonate and anhydrous sodium hydrogen carbonate. It is important for these two substances to be available in the anhydrous form as they are free of water content. Anhydrous compounds, such as sodium carbonate, are prepared by simply drying in an oven until all water content has been removed. Secondary standards are solutions whose concentrations have been determined using titration with a primary standard solution. You may have come across titrations that use standardized sodium hydroxide solution. While sodium hydroxide is not suitable for a primary standard because it is hygroscopic, we can actually performing a titration to determine its concentration. This process is called standardization. This involves titration of the sodium hydroxide with a primary acid standard, such as a hydrochloric acid solution with an appropriate concentration. Once the titration allows us to determine the sodium hydroxide solution, this will become what we call a secondary standard. Although secondary standard solutions can be used, we try to avoid it because the process of standardization will introduce more errors in the experiment, and this will in turn affect the accuracy of your final result. An experiment is conducted to investigate the concentration of a solution of hydrochloric acid. So this is my unknown solution. Exactly 50 ml of the hydrochloric acid is required to neutralize 20 ml of a 0.05 mol per liter solution of sodium carbonate. So because we know the concentration of this solution of sodium carbonate, this is my standard solution. Specifically, this is my primary standard because I've prepared it without standardization. Calculate the concentration of a hydrochloric acid solution. Before any titration, it's important to write a balanced chemical equation to represent the actual neutralization process that has taken place. So here I've got the reaction between an acid and a metal carbonate, which produces a salt, so sodium chloride, water, and carbon dioxide gas. For this particular reaction, we have to balance it by adding 2 in front of sodium chloride so that there's 2 sodiums on both sides, and then adding 2 in front of the hydrochloric acid so that the number of chlorines are also balanced on both sides of the reaction. The number of sodium chloride required is equal to its concentration multiplied by its volume, which we get as 1 times 10 to the power of minus 3 moles. The moles of hydrochloric acid in this case is twice the number as the moles of sodium carbonate, and this is due to a 2-to-1 reaction ratio as shown in the chemical equation. The concentration of hydrochloric acid is therefore the moles divided by volume, so 2 times 10 to minus 3 divided by 0.05 liters, and this yields a value of 0.0200 mole per liter. And I'll also leave this as 3 significant figures. Let's use that example to go through the process of preparing a standard solution. We'll focus on preparing a primary standard solution. So as we discussed, the sodium carbonate is our standard solution. Sodium carbonate usually comes in solid form as it is an ionic compound. So the first step is to weigh out an appropriate amount of sodium carbonate, dissolve this solid in a clean beaker, and once we have the solution of sodium carbonate, we'll then transfer this into a clean volumetric flask in which we can add additional amounts of water to reach our desired concentration. So our desired concentration of the standard solution is 0.05 mol per liter. Even though we only want 20 milliliters of the solution, we ideally want to make a much larger volume, for example, 250 milliliters. In a titration, you want to repeat the neutralization process many times to achieve consistent and reliable results. And as we'll discuss in a moment, some equipment will have to be rinsed and cleaned using the standard solution. So by preparing only 20 milliliters, it will not be sufficient. For the sake of simplicity, let's just say in this titration, we are preparing 250 ml of a 0.05 mol per liter solution of sodium carbonate. So first, we want to calculate how many moles of sodium carbonate do we actually need in the solution. So we can multiply the concentration by the volume, which is 250 ml. This gives you a number of moles of 0.0125 moles. Because the sodium carbonate comes in a solid form, we can achieve this exact number of moles by finding the corresponding mass. And this is calculated by multiplying the moles by the molar mass. The molar mass of sodium carbonate is as shown here, and this gives us a value of 1.325 grams. This is the exact mass of sodium carbonate that we want to weigh out before producing a solution. The second step after you weigh out 1.325 grams of sodium carbonate is to add distilled water to the beaker slowly. It is important to use distilled or deionized water in titration because we don't want any other ions that's present in normal tap water to interfere with our neutralization reaction. We want to make sure we avoid any splashes, as this may lead to partial losses of the sodium carbonate in the solution, which will then lead to an inaccurate concentration. To help with the dissolution process, you can use a glass stirring rod to make sure that all solid forms of the sodium carbonate is completely dissolved. Once the solution has been properly made in the beaker, you can then transfer this into a volumetric flask using a funnel. However, before you make the transfer, ensure that the volumetric flask has been properly cleaned and rinsed with distilled water. We can use distilled water to prepare the volumetric flask because we'll be adding distilled water to the already made solution to achieve the right concentration. After the transfer of the solution from the beaker, make sure you also rinse the funnel and the beaker with distilled water as well, and discard the rinsing into the volumetric flask. This is to ensure that we are achieving a complete transfer of the sodium carbonate from the beaker in the volumetric flask. If we are leaving some amount of sodium carbonate behind in the funnel or the beaker, then the concentration of the sodium carbonate will be slightly lower than what we want it to be. In the volumetric flask, there's always a very clear line that indicates where the water level should be filled up to. This is known as the graduation mark. Volumetric flasks come in different sizes. For a 250 milliliter flask, the graduation mark will indicate where the volume will reach 250 milliliters. When you're adding distilled water to the indicated graduation mark, make sure you add water through the funnel until the water level is approximately 1 centimeter below the graduation mark. After this point, remove the funnel and add distilled water dropwise until the bottom of the meniscus, so this is the bottom of the meniscus, reaches the graduation mark. It is important for you to complete the process by adding the distilled water dropwise, as you want to avoid over adding beyond the graduation mark. In cases where you over add the water beyond the graduation mark, you will need to remake the whole solution, as pouring out small amount of excessive water from the solution will risk losing some amount of the standard, such as sodium carbonate. Once the distilled water is added to the right level, you can then stop at the volumetric flask and homogenize the solution by inverting the flask up to 10 times. To summarize the whole process of preparing a standard solution, first we want to calculate the right amount of standard that we need to achieve the desired concentration. We'll weigh out this amount on a scale in a beaker. We'll then add some amount of distilled water to the beaker to achieve a solution. This is then transferred into a volumetric flask. The volumetric flask is then added with distilled water until it is 1 centimeter below the graduation mark. Afterwards, further amounts of distilled water is added dropwise until the bottom of the meniscus reaches the graduation mark. The flask is then stopped, inverted a few times to achieve a homogeneous solution. This is what a typical titration set looks like. We have two components. We have the burette and we have the conical flask. The burette is a piece of volumetric glassware that usually ranges from 0 to 50 milliliters on its marking. And on the burette, there's usually 0.1 milliliter increments as shown here. In titration, the titrant refers to the solution that will be added to the burette. The titrant can either be the unknown solution that you're trying to determine the concentration of, or it can be the standard solution. The burette should be rinsed with distilled water, followed by a small amount of titrant. Both the distilled water and the titrant should be evenly coated on all surfaces of the burette and then further discarded by the tip of the burette. It is very important to finish the rinsing process with a small amount of titrant because any leftover amount of distilled water in the burette will lead to the dilution of the titrants, which leads to a lower concentration of the titrants. If you're adding the unknown solution into the burettes, then the solution's concentration will be diluted. If you're adding the standard solution to the burettes, then the concentration of the standard solution will also be diluted by the small amount of residual water that's left over after the rinsing process. It is okay for a small amount of titrants to be left over after rinsing, because a titrant will have the same concentration as the titrant that you're about to add in. Any residual amount of titrant will not affect the concentration of the titrants that will be in the burettes. Suppose for a titration, the burette contains the acid solution. The conical flask will then contain the base solution. And in our previous example, the base solution will be the standard solution of sodium carbonate. So the next step in titration is to use a clean pipette to transfer the standard solution from the volumetric flask into the conical flask. Now, we'll not be using the whole volume of the standard solution. We'll be only using a small volume. The volume that we can use is 20 milliliters. This volume is known as the aliquot, the amount of the standard solution that's used for each titration trial. Make sure the pipettes are rinsed with the standard solution prior to use. In general, the pipettes should be rinsed with the chemical that is about to be transferred using the pipettes. So if you're transferring the standard solution from the volumetric flask into the conical flask, then pipette should be rinsed with the standard solution. You should not rinse the pipette with distilled water only, because any residual amounts of water left over in the pipette will then dilute the concentration of the standard solution that you're transferring, and that will lead to a decrease in the number of moles of the standard that you're transferring into the conical flask. The conical flask is rinsed with distilled water prior to use. In this case, it is okay to rinse the flask with distilled water because dilution of the standard solution will not affect the number of moles of the flask. As long as you appropriately use a pipette to transfer the right volume and the number of moles of the standard solution into the conical flask, any dilution with water in the conical flask will not affect the amount of the standard that's already in the flask. A good way to understand this is imagine you have a glass of orange juice. If we add some amount of water to the orange juice, this will dilute the orange juice, but then the total amount of orange juice that's in the glass will remain the same. The conical flask can either contain the unknown solution or the standard solution. In our example, the burette will contain the unknown acid solution, so the conical flask will contain the base standard solution. However, the opposite can also work. The burette can contain the base standard solution, while the conical flask can contain the unknown acid solution. So to summarize, the volumetric flask used to prepare the standard solution is to be rinsed with distilled water. The pipette is rinsed with the sodium carbonate solution because we're using the pipette to transfer the standard solution of sodium carbonate from the volumetric flask into the conical flask. The conical flask is rinsed with distilled water, and the burette is rinsed with a titrant solution. And in our example, the titrant solution will be the unknown hydrochloric acid solution. Once you have set up the burette with the titrant, the conical flask with the right amount of the standard solution, you can then add a suitable indicator to the solution and place the conical flask over a white tile to visualize the color of the indicator better. I discussed how to choose a suitable indicator for titration in its separate video with titration curves. This concludes the video on preparing for titration.